Okay, so we take this space y is equal to x minus a, then we work on this space y. On this y, fn converges to f throughout on for each x in y. Okay, so we can assume that this fn x, it converges to fx for each x in x. We take this assumption here. Now for each for each pair of positive integers n and k, for each pair of positive integers, for each pair of positive integers and k, n and k would define this set E and K. E and K, which is equal to x belongs, it's the subset of E, such that mod of fmx minus fx is less than 2 power minus n for all m greater or equal to k, for all m greater or equal to k. Now you can see this this set is measurable. Why it's measurable? Because let me explain it how it's measurable. Okay, let me explain it here. Suppose this f is a measurable function. Then the set fx such that mod of fx less or equal to a is a measurable set. Then the set x belongs to the x such that this holds mod of fx whenever f is a measurable function. Why it's measurable? Because this can be written as it's equal to the x belongs to x such that minus a less or equal to fx and less or equal to a. So you can see this is actually the inverse image of closed interval minus a to a. So since f is measurable function, therefore inverse image of closed set is measurable, and minus a to plus a, this closed interval is a closed subset of R. So therefore its inverse image must be measurable. So that means this is measurable, and this is equal to that set, and this is here. It's a measurable set. And here you can see this fm is a measurable, so you can fx is a limit of fnx. So that means both fmx and fx, they are measurable functions. So their difference is a measurable function. So this is your function f actually, fmx minus fx. You can treat this as gx. Gx is a measurable function, and it is mod of gx less than 2 power minus n. So it is here strictly less. If I ever replace this less or equal to, but strictly less, I will get the inverse image of open set actually here. Let me erase this. Okay. If it's strictly less, then it will be equal to here. It will be equal to here inverse image of an open interval. Okay, it will be like this. It will be here less than, and this is a open interval here, not closed. An open interval is an open set, so therefore it's an inverse image of open set. Since f is measurable, so that means inverse image of every open set is open, so which means that this set is open. So whenever f is measurable function, then the set x such that mod of fx less than a is always measurable for each a. And here fmx minus fx is a measurable function, therefore mod of fmx minus fx less than 2 power minus n is measurable for each n. So which means that a and k is measurable for each n and k. So there then E and k is a measurable subset of E for all n and k. It's a measurable subset of E for each n and k. Also, we can see that it's increasing, so you can, this E and k is increasing with respect to k also. E and k is subset of E and k plus 1. it follows from definition, by definition of ENK. Okay, by definition of ENK, you can see, you can apply the definition here. You can see ENK is subset of ENK plus 1. I will write here this ENK. What's actually ENK? ENK is this set here. Then I will try to explain it how it's increasing with respect to K, such that mod of fmx minus fx is less than 2 power minus n, where m is greater or equal to k. So suppose suppose x is in ENK, we will show that x is also in ENK plus 1, because we need to show that ENK is subset of ENK plus 1. So whenever x is in ENK, then this is true for each m greater or equal to k. So whenever it is true for each m greater or equal to k, then it will be true for each m greater or equal to k plus 1. Because anything which is true for, suppose, greater or equal to 2, it is also true for greater or equal to 3. So if whenever x is in ENK, it means that x belongs to ENK plus 1. So that means this ENK is subset of ENK plus 1. So it's very simple. It's very simple. Let's apply this definition of ENK. Apply the definition of ENK. Yes. It's an increasing sequence of measurable sets. So ENK is increasing sequence. It's true. Now, since limit of f and x is x, since f and x converges to fx, limit of f and x is x for all x. So it follows that it follows that ENK converges to it will converge to the union of ENK, k runs from 1 to infinity, is equal to E. It's equal to E. Because this f and x, it converges to fx for each x next. You can easily verify this. The union of ENK. Let's take any x in union of ENK. It is in one of the ENK for some k. And then this whole is fmx minus fx less than epsilon. So you need to show that this. Then you can apply the limit and approach to this m is approaching to infinity. It's true. Okay, it's very simple actually. Let me try to explain this. Let's actually we need to show that this ENK is subset of E for each k. Then its union will be equal to E, because E is always subset of ENK. ENKs are subset of ENK are subsets of E actually. So we just need to prove that ENK is subset of E. So let's verify this. Let's verify this. Let x is in union ENK, k runs from 1 to infinity. This implies x belongs to ENK for some k, okay, for some k. So whenever x is in ENK, this means that that by definition of ENK, this means that mod of fmx minus fx is less than 2 power minus n is less than 2 power minus n is less than minus 2 power n for all m greater or equal to k. So m is any integer greater or equal to k, where k is a fixed number. So letting this m sorry, actually we need to show that E is subset of union, not union is subset of E, because union is always subset of E. Sorry, it's a mistake here. So we need to show that this E is subset of the union. We choose any point in E. We show that it is in some ENK. Okay, we show that this. We show that this one. We show that E is subset of union A and K runs from 1 to infinity. Okay.